Today we'll be doing a free response from 1989, a rectangular loop of wire resistance R and dimensions H and W moves with a constant speed V towards and through a region containing a uniform magnetic field of strength B directed into the plane of the page. The region has a width of W as shown in this diagram. Part A asks us for the interval after the right-hand edge of the loop has entered the field, but before the left-hand side of the loop has reached the field. And it asks us to determine the magnitude of the induced current in the loop. So they're asking us for the induced current. We know that I is equal to E over R. And in this instance, E is equal to B LW over R. Now we simply have to substitute L in for H, and we have BHV over R, and that is part A, 1. A2 asks us for the magnitude of the applied force required to move the loop at a constant speed. So the basic equation for force is F is equal to Q VB sine theta. However, in this case, Q can be I, LB sine theta. These are usually the two equations you go to when you're looking for force and magnetic field, and in this particular instance, the second formula makes more sense. So we found I in the previous example, and we simply plug in. We said that was BHV. L once again is H, and we have B again, divided by BHV divided by R. And so our final answer is B squared H squared V divided by R. Part B asks us to find the induced current I in the loop and to graph it as it progresses through it. So for this, we're going to use a right-hand rule. The magnetic field is into the board, and the velocity is to the right, right? So as this loop goes in, it's going to experience a current going in this way, so the clockwise direction. And so it's going to respond to restore the balance, and therefore it's going to go in a counterclockwise direction. So this is for the part between W and 2W because of the right-hand rule. Then from 2W to 3W, the entire loop will be facing a constant magnetic force, so it's going to go back to 0. From 3W to 4W, the loop is exiting. So the magnetic field, which was going inside, causing an increase, is now going to come out because as it leaves, it experiences less of a magnetic field. So it's leaving, and the induced current is now counterclockwise, and so the loop is going to react with an opposite and equal current, which will be clockwise. And that's why it will go here. And once it exits, it will no longer face an induced current and return to equilibrium and without an induced current. And that's basically how the graph looks there. For part B2, they want to know the applied force required to keep the loop moving at constant speed, and they say have the positive be the right side and the negative be left side, the negative part of the axis. We can see from this that the velocity is to the right, and F is directly related to velocity, so it will never have a force to the left. It will constantly be to the right, and just like the induced loop, it will have a similar pattern. However, it will remain over the x-axis. And that is all for this free response. Thank you.